Log on, tune in, find out. Another good idea from Cambridge.
Thank you very much, and thank you for the invitation to this activity. It's a pleasure being back at the Newton Institute. What I would like to report on today is joint work with Sam Kruszewski. The paper is not yet on the archive, but I hope we'll be able to put it there very soon. So let me give a short introduction. So, and I suppose this will be very well known, if we have x in P4, and everything for me will be over the complex numbers. It's a smooth cubic threefold. And then Clements and Griffith, while proving that these are non-rational, they introduced the intermediate Jacobian I of x, which we can write it h21 of x, h30 is trivial, divided by h3xz. And that's not just a torus, it's an abelian variety, and it's a principally polarized abelian variety of dimension 5, so it's a point in A5. This is the intermediate Jacobian. And in this situation, one has a global Torelli theorem. So we have a global Torelli theorem, and this means that if we look at the smooth cubics in P4, modular projective isomorphism, we can embed it into A5 by associating, sending x to I of x. And let me call this I, and I want to think of I as a subset of A5. It's locally closed. And a question, and that was the starting point of our considerations, which was posed by van der Heer, asked about the class of this set, or its closure. So what is class of, say, I bar, meaning closure in A5, in the Chowring of A5. Can one describe it? We can say something about this, also about the closure in some compactification. We can't quite answer that question, as you will see. But to describe this, so let me recall what the Hodge bundle is. Several ways of saying that. We can look at the, say in a stack sense, universal family. Pi. And then we can look at the bundle E, which is defined as P lower star of omega 1 x over AG. That's a rank G vector bundle. And we define lambda I to be the ith Churn class of this bundle. And then these lambda I generate what's called a tautological ring. And what we have are relations on AG. On AG we have that lambda g is 0, and we have that 1 minus lambda 1 plus lambda 2 plus minus lambda g, 1 plus the 1 plus lambda 2 plus lambda g is 1. Okay, and what we also note is we can extend E and hence the lambda E to any toroidal compactification. Of AG. Then the first relation, the lambda g, that is no longer 0 then. But the second relation will still hold. Okay. So let me state our first result. What we can prove is this. We look at the class of I and then take the closure in A5, union A1 cross the theta null divisor on A4. So the theta null divisor is where one even theta constant vanishes. And that's a subset in A4. A1 and A4 I consider as sitting in A5. And the class of this is the following. And I'll write down a general formula because that's much more instructive than the special formula. But we want to then evaluate that at g equals 5. It's 2g minus 1, 2g minus 1. Sum I equal to 0, g, lambda g minus I, lambda 1 half to the I. So that's what we can prove for this class. And we can do this more concretely. So using these relations, for example, this is on A5. I'll say something about the compactification in a few minutes, but this is an equality in A5. So if we work it out, if we use these relations, then A bar union A1 cross theta null is 93 times 4 lambda 1 square lambda 3 plus lambda 1 half to the power of 5. And so that's in codimension 5, and I should have done that dimension count first. So let me recall it now. So the dimension of I, so this is the number of cubics, so this is 4 plus 3 over 4 minus the GL minus 25, that's 35, minus 25 is 10, and the dimension of A5 is 5 times 6 over 2 is 15, so the codimension is indeed 5. Okay. So that's that. But now there is, of course, the natural question, which was just asked by Valerie, namely, what about compactifications? So, and I want to work here with the so-called perfect cone compactification. Prof. So this is the perfect cone compactification. It's atoroidal compactification. And well, one meaning of it is if G is at least 13, then this is a minimal model in the sense of minimal model theory as it was proved by Nick. 12. Okay, thank you. Okay, and then I also want to look at the level 2 cover. And I also want to recall boundary components of AG perf 2 correspond to vectors n in z over 2z to the 2g minus the origin. Okay. So given that, can one read that over there, or is that bad if I write there? It's okay. So let me state theorem 2 also by us. We have in A perf the following. So we now take again I union A1 cross 4. Take the closure of that. This is 1 over n. So I should say what the capital N is. It's the order of the group sp2g z over 2z. Of course, one can write down an explicit formula for this, but that doesn't matter. Times. Well, let me write it like this. It's going to be a bit longer. I take all elements in z over 2z to the 2g, which are odd in the sense of odd 2 torsion points. So if I write it as m1, m2, then m1, m2 is, the product is 1. Sum over I equals 0 to g, p lower star, and I write something on AG2, yeah, on the level 2 and push it down to the one without level structure. Then the g minus I from the 1/2 minus 1/4. So again, this has to then be specialized to the case g equal to 5. Delta n, sum over delta n, where the n goes through z to z minus 0, such that n plus m is even. Okay? That's the formula. Sorry? Yes, thank you. Thank you, yes. That should be to the ith power. Okay, and I'll try and explain to you where such a formula comes from. And as you can see, I mean, this is more general. It doesn't just apply to A5, and I'll try and explain to you where it comes from, what it means. Sorry? M odd. So think of a two torsion point. And you know what an odd two torsion point is?
Oh, okay, so you're just choosing some
Okay, so the way we can tackle that, so let me say, geometric approach. Okay, so say A of theta, let's that be a principal polarized abelian variety, and we assume the theta divisor is symmetric.
Could we just ask again, just to make sure? So
Yes.
first of all, there's a little typo. I mean, the last z over 2z, that should be to the 2g.
Yes, thank you.
And then still, what does n plus 2m plus m even means? Do you fix an abelian variety?
Well, let's put it this way. For
look
any
at the theta characteristics on a fixed abelian variety.
Well, let me do it like this. Take any vector in here.
Okay.
Yeah? Write it as k1, k2. And I can multiply k1, k2, and I can ask whether that's 0 or 1. Call that even and odd. And then A of 2, two torsion points. And then following theorem of Clemens and Griffith, the theta divisor I of x has a unique triple point. And that then must necessarily lie at an odd two torsion point. And then later on, Mumford noticed that one can recover the x itself from that triple point. So x is proj of the tangent cone at this point. And finally, and that's sort of very important for our way of approaching this, there is a result of Casalena Martin, one person, and Friedman, which says that among the indecomposable Jacobians in genus 5, the existence of a triple point characterizes the intermediate Jacobians. So let a theta be indecomposable. then a theta is an intermediate Jacobian if and only if theta has a triple point. Okay. So that's the geometry, and now we will do a certain amount of theta functions, because in a way that can then be linked to gradients of theta functions, and that's what allows us to get a hold on the class of these cycles.
Does that mean they prove that the locus of triple points can't have dimension 1?
Sorry?
Does that mean they prove that we can't have a curve of triple points? Or do they assume that triple points are so?
Not among the indecomposable ones. So we have theta functions. So the usual setup. So the upper half plane, see the upper half plane. Complex C by G matrices, symmetric, positive imaginary part. And then we have the group gamma, which is SP2GZ, whether G or 2G is always a matter of notation. That acts on a G in the usual way. If I have a gamma and I write it in G by G blocks, and tau is mapped to a tau plus B, C tau plus D inverse, and analytically AG is just the quotient of AG by this group. And we also need some congruence subgroups. So gamma Gn, or G in gamma G. G is congruent to 0 mod n. So this is a full level n group, subgroup. And we need, for technical reasons, because of the theta constants which are implicitly in the picture, we need the group gamma Gn, 2n, which is all gamma in Gn, with diagonal A transpose B, congruent diagonal C transpose D, congruent 0 of 2n. And we look at the quotients, say AGN, G by this group, full level group, and similar Gn 2n, which is Hg by gamma G and 2n. Okay, continue here. We need the Riemann theta function. So this is theta tau z. That's the sum over all n in zg e to the pi n transpose tn plus 2 pi n transpose z. And that's the holomorphic functions on the upper half plane cross CG. And we, given a point in the Siegel space, we define a torus in this way. So we take the lattice spanned by the unit vectors and the columns of our period matrix, and then theta defines a principal polarization on 80. That's all very well known. And what are the two torsion points? Two torsion points I can write as m t epsilon plus delta over 2. The epsilon delta are in 0 or 1 g, and then what I said before, m is even odd if epsilon delta is even or odd. And what we define is then Fm, a function of tau and z. This is defined as the gradient with respect to z of theta at z equals n. Well, we can do this. And we get the following lemma. So this is a vector valued function, and I can ask whether that's a modular form, whether it's a vector valued modular form, and the answer is this. If I am on AG at least 4n, so I need some level cover for that to hold, then this is a section in the following vector bundle, determinant of the Hodge bundle, 1/2, meaning I take a root of the determinant of E, and the one we take here is the one where the theta constants are sections of, tensor E. Okay, that can be checked very easily. And then the group g of 2 divided by gamma g for 8 acts on the gradients by certain signs. And hence what I can do, I can define Gm, or G epsilon delta if you prefer, as the set of all tau, f and tau is 0. I can think of that as a set in AG2. And the meaning is theta divisor has a triple point at n. And then I can push that down to AG. So we define IG as P of this set, and that now sits in AG, and this is independent So what we're looking is abelian varieties whose theta divisor has a triple point at some odd two torsion point. And the M here should be odd. Otherwise I don't get anything. Okay. And then what we clearly have is that the codimension of this set AG is at most G. Because it's a section in a rank G vector bundle, a zero set of a section in a rank G vector bundle, there is a conjecture due to Sam-Kruszewski and Salvatimani which says that the codimension of this set is always G for every G. I should say G greater than or equal to 3 because otherwise it's empty. And this is known for small values of G. Again, Kasa, Lena, Martin and Friedman, they didn't write it in this way, but it follows from their work. This conjecture holds for G at most 5. In general, it is open. Recently, Sam and I came up with another proof for that, which is purely in terms of theta functions and abelian varieties. But originally, this is due to these authors. So what does that mean for small values of G? I want to keep this because I'll then come back to this. G, first of all, IG is empty, for G less than or equal to 2. Then I3, that is just sim 3 of A1, sitting in A3. A4, that is then A1 times the theta null divisor in genus 3 in A4, and A5 is the closure of the locus of intermediate Jabobians union A1 cross theta null. Genus 4 sitting in A5. And that's not just as sets, this holds as schemes, I mean reduced scheme structure. Yeah. So the Fm generically do not vanish with higher multiplicity. Okay. And then once one has that, the proof of theorem 1 is actually very simple. So the class of A5, or I should say the class of A bar union A1 cross theta null 4, it's the same as the class of A5 are just nothing else but the fifth Chern class of this vector bundle of determinant of E root of the power of 1/2 tensor E, and then compute. That's easy. Now things get naturally more complicated when we go to the boundary. So let me discuss this. And this is where the technical difficulties then lie. For technical reasons, I want to work on level 8. Perfect cone compactification, level 8. And then, again, for level 1, the boundary is irreducible. But for higher level, of course, we get several boundary components. We already saw that for level 2. Again, here we have several boundary components, and we can enumerate them. Components correspond to primitive, I'll say a word about this in a second, vectors plus or minus n. I mean, plus and minus n give the same boundary component in z over 8z to the power of 2g minus the origin. So what's primitive? So choose some representative in z, and then the GCD of the entries, yeah, together with n should be 1. Yeah? That's meant by primitive. And of course, for level 2, that's not really a condition, and then also plus minus don't play a role. But this is what the general, this is not just true for 8, this is true in general. And then the crucial observation is this. Proposition, sections Fm. Now let me pull it back to level 8. It's a little bit easier. E extend sections. I already told you that the vector bundle extends, yeah? But we can also extend the sections, so to sections F tilde of M. Now these are sections on perfect cone of level 8. And the bundle which we get is determinant E 1/2 tensor E. And now we should subtract certain boundary components, and one has to figure out which ones. So we subtract sum over the following boundary components dn, where plus minus n is in z 8z g minus 0 primitive, and n2 plus m is even. So I didn't tell you what n2 is, so let me do it here. n2 is n mod 2. Yeah? Okay, you could of course say, well, why subtract these boundary components? You still get a section, but what we now get is this, and this section does not vanish at the generic point of any boundary component. Okay. Well, that's essentially looking at limits of theta functions, writing down coordinates in the neighborhoods of boundaries and figuring out what the Fourier expansion is, and then one can derive this result. And then, similar to before, define for certain sets, so G, M, G, say bar F M tilde equal to 0. This sits in here, and then we project down to level 1. So this is in AG. Perfect. Okay. Now what we get, and that's essentially by construction. Yeah. Sorry? Here? Here? Oh, I forgot something. No, I didn't forget. No, there is an M here. It's hidden here. N2 plus N.
N is a 2 or N?
N2, which is the mod 2 reduction of this vector N. This is, yeah. Yeah, and the M is here. Yeah. Okay. So what we have by construction is that the closure of our set IG is in this set. But it could be bigger. However, we don't think so, or we don't hope so. Let's have a conjecture. J bar is equal to this, and has pure codimension G. For all G. So that's what we hope, and what we can prove is theorem this holds for genus at most 5. That's actually technically hard, at least, well, no, I think it just simply is technically hard. So what we do, or what's the idea here? The idea is this: we must make sure that G bar does not pick up extra components on the boundary. There's no problem in the interior. sets are obviously equal. Yeah. And what we do is for this we study degenerations of abelian varieties and the gradient of the theta function, and these come also with theta divisors, at odd two torsion points. So what's behind there is that perfect cone and second Voronoi cone compactifications, they are not the same. But in this case, for small g, one knows the difference. And for our purposes, they're close enough. So for second Voronoi, we have this interpretation of boundary points as degenerate abelian varieties due to Valery. And so there we can study these degenerations. We can look at the theta divisor. We can look at gradient at two torsion points. And we must make sure that this is also the same as restricting these functions here to these points. Yeah? There's quite a bit of subtlety there. But eventually we can do it. So this also then involves a study. So a study of degenerations of abelian varieties of null torus rank. And of course there is the work by Valery Alexeyev. We actually prefer to sort of do it by hand here. I'm sure you could also follow from your general machinery. We found it a little bit easier for us to just work it out by hand at that point. But there is certainly a certain amount of work involved in this. But once one has that, yeah, then the proof of theorem 2 that is then very easy, because what we then get the virtual cycle if it's in the right codimension, and for g less than or equal to 5 we know, is then just Cg of this bundle tensor E tensor O of minus dn, where the summation is as above. Yeah? And that's then just again a computation. And so what you can see here is, so this is read on a G perf. So what that means is we can have a singularity at any two torsion point. Yeah? That's why we add over all these two torsion points, odd two torsion points here. And this, that's just a question of the ramification between level 2 and level 1. But you'll recognize from this description here the structure of this formula. And this is where it comes from. So again, once these technical difficulties are done, then the proof is essentially computational. Okay. And to conclude, let me discuss a few, that's the last point, probably 5. some low genus cases. Well, the first thing where something happens is in genus 3, and then the chowering of A3 perf, we know this, yeah? This was computed by Van der Geer. And that also gave us a good check for our method. So we have G3, take the closure of that, and that is, well, the same as I3, but it's sim3 of A1, take the closure of that. And that is the following expression, minus 35 lambda 3 plus 35 over 2 lambda 1 cube minus 25 over 4 lambda 1 square sigma 1. I'll tell you in a minute what the sigma is, plus 5 over 8 lambda 1 sigma 2 plus 12 over 8 lambda 1 sigma 1 square minus 112 sigma 1 sigma 2. So the lambdas are clear. What are the sigma? Here sigma I is the ith elementary symmetric polynomial of the boundary components on some level cover. There we have several boundary components, so that makes sense. Pushed down to a 3 perf, which by the way is the same here as second volume. Okay, so that was a check for us whether it came out, and it didn't.
You had somehow not all boundary components, but you had this even condition. So
Yes,
how does that work?
but then once you sum over all m, yeah, you must get something which lives downstairs, yeah, and this is why it's only the symmetric polynomials which appear. But here it's correct, yeah. Yeah, I mean, this is not symmetric, so to speak, but if you sum over all m, it becomes symmetric. Okay, so actually it didn't come out. So we were quite frustrated. In the end, we found a typo in the printed version of Van der Geer's paper. So once the typo got corrected, it was then the same formula. That was a simple typo. Okay. Then genus 4. So what we get is A1 cross the theta null divisor, genus 3, class of the closure, that is 180 lambda 1 lambda 3 plus 45 over 2 lambda 1 to the 4th plus I want to spare you that 15 further tops, yeah, in these sigma and yeah, etc. Okay, what it does check out quite nicely is by other means. One can compute the projection of this class to the tautological subring. So the tautological ring is a subring, but in each degree we have a perfect pairing, so we can project to the tautological subring. That was something pioneered by Faber and van der Heer. And then if we do that, we come out, and that's a totally independent calculation. We come out with this. Now, there are two possible, I'm at the moment not absolutely sure how to interpret this. There are two possible scenarios. One is this class is not tautological, and the other is that sum here is orthogonal to the tautological ring. I don't know which is true. There are certainly summands in here which are not orthogonal to the tautological ring. But I do not know whether the entire sum is. That could still be the case.
Isn't by your definition computation, isn't it in the tautological ring?
It depends now what we call the tautological ring. If we call the tautological ring the one of where just the lambdas are, then so here we also have boundary components. If I just define the tautological ring as van der Heer and Faber do as the one generated by the lambda I, then it's not.
It's 18 or 180?
180. Okay. But in a way, I mean, you could say that this is in the tautological ring on the compactification if you allow the boundary components. Okay, and final one. Genus 5. So what we get here is we get 5 bar, I5 bar, I bar union A1 cross 4. Okay. And that is then 496 lambda 5 plus 372 lambda 3 lambda 1 square plus 93 over 2 lambda 1 to the 5th plus many summands supported on the boundary. Okay, that's the same. So if we just work in A4 and A5, then these classes are tautological. Okay. Anyway, that's a huge sum, and one can sort of interpret some of these summands here in this boundary geometrically, but I certainly don't want to write this down. Okay, that's as much as I wanted to say. Thank you very much.
Any questions?
These symmetric polynomials in the boundary classes.
Yeah.
Like the sigma 1, for instance, when you push it down to the level 3
Yeah.
modular space, you don't just get some multiple of the boundary divided out?
Yes, you do. For sigma 1, sigma 1 is just the boundary, but sigma 2 it gets more interesting, because then essentially what you get is, well, okay, so what you can then get on the level structure, you get the intersection of these boundary components. Downstairs it's then, in this case, but if you go deep into the boundary it gets more complicated. It is then the part, say we are in A3, boundary lives over A2, and then the sigma 2 lives over A1 if I look over the Satake compactification. But then things get more complicated if I have triple intersections. Yeah? Say if I have 3 devices, there are 2 cases then. These devices can then intersect, say I'm an AG, they can intersect in something which lies over AG minus 2 or AG minus 3. Yeah? And the more there are, the more possibilities there are. Yeah.
Take these loci and restrict them to MG. Is there a similar kind of geometry?
To MG,
So you have these
yes.
varieties in AG defined by the vanishing of a gradient variety.
I can certainly restrict them to MG. I must admit, it's a good question. I must admit, we just simply haven't thought about it. It's certainly a valid question. Yeah.
Any more questions? In that case, let's thank the speaker again.